Hi, everybody. Welcome to the Allele of the Day on Love Goes Live, where we explore and today celebrate the diversity of human genetics. If you need a refresher or primer genetics, be sure to watch Genetics Primer, 4 Ideas in 4 Minutes, which is on this channel as well. And if you're enjoying the content, please subscribe so I can really stop spamming friends with emails telling them to watch these. Okay, without any further ado, let's look at the allele of the day. And let me start by sharing my screen as I always do. Okay, here we go. All right, so today's story is about an athlete from Finland named Eero Montaranta. And he was the greatest, or still is actually the greatest Olympian from the country of Finland. And he was to Nordic skiing what the Badger or Eddie Merckx is to professional cycling. And that is during his time, so he was from 1960 to 1972, he was pretty much reigning champion, went to the Olympics 4 times, medaled 7 of those times. And it wasn't just that he beat everyone, it's how much he beat everyone by. So he still holds the record in the 15-kilometer classic of winning by 40 seconds, which has not been met since. And as these things often go, when you have an extraordinary performance, sometimes people start looking around, and he was eventually accused of blood doping. And he was accused of blood doping because they took a blood sample and they measured what's called hematocrit. Now, so hematocrit is more or less the percentage of red blood cells that's in a sample. So if you take out 1 ml of blood and 45% of it is red blood cells, your hematocrit is 45. The average person has a hematocrit of 40 to 45, okay? In professional cycling, it used to be that if your hematocrit was above 50, you were accused or suspected, maybe not accused, but suspected of doping. And if you remember Lance Armstrong and US Postal scandals of the beginning of the 21st century, their hematocrit was typically somewhere between 55 and 60. Okay, Eero's hematocrit was typically around 60 to 65, so almost 50% higher than normal. So he was, of course, accused of blood doping, and then he was vindicated in 1993 by a group of scientists who went and looked at the genetics of not only him, but of his entire family, and they published it in one of the top-tier journals, the Proceedings of the National Academy of Science, which is sponsored by AAAS. All right, so the star of our show is going to be a signal molecule called EPO, or erythropoietin. And EPO is, of course, the drug that endurance athletes take, but it is really a cytokine that is produced in all of our bodies. And it does the following. So it is produced in the kidney. So your kidney produces EPO. It secretes it into your circulatory system, where it goes to bone marrow. And in the bone marrow, you have stem cells that are then induced to differentiate into red blood cells. Right, so if we were to zoom in on what's actually happening inside of the bone marrow, you have EPOs coming in. EPO is going to bind to the EPO receptor. This is in a progenitor cell. So this is essentially a cell that hasn't taken on a fate in its life. It will activate the EPO, will bind to its receptor. It'll activate the red blood cell program. The cell will start to divide, and it will eventually become red blood cells. So essentially, if you take EPO, you increase, or if your body is making EPO, you increase the amount of red blood cells. All right. So what this group found is when they started sequencing and looking at genes within Eero, they found, if you remember the concept of SNP, single nucleotide polymorphism, they found on chromosome 19 in the EPO receptor at the 6,000th nucleotide, a G got changed to an A. Now, what does that really mean? You're changing one nucleotide. What does that mean? Well, it turns out that that one nucleotide ends up affecting the EPO receptor, so it is stuck in the on position. What that means is you no longer need EPO. So this cell, these progenitor cells, which were in Eero's bone marrow, were always active. So the red blood cell program was always active. Those cells were always dividing. And so hence he was producing red blood cells at a super high rate. Right? So he was not blood doping. He was born this way. And even more interesting is they did a family pedigree. This is not his entire family pedigree. They actually looked at 200 individuals. And squares are males and circles are females. So let's just start this generation. So this genetic relative carries that EPO receptor mutation, so it's naturally blood doped. This son is, this daughter is. And then if you look over here, you had a brother whose son had it and whose granddaughter had it. And so it seems to be dominantly inherited, and a good percentage of his family carries it. All right, let me stop sharing the screen for a second. So this is really interesting. And if you watch the primer on genetics, you know, one of my favorite sayings is that most of the time it's probabilistic, not deterministic. So does carrying this rare allele for the EPO receptor make you a world-class athlete? No. It is not deterministic. In fact, most of his cousins and most of his relatives are not world-class athletes, although some others are, but most are not. So carrying it doesn't necessarily make you a world-class athlete. Does it increase your probability? Yes. By how much? I don't know. That's sort of hard to measure. It also comes at a cost, because if you have a hematocrit at 65, the probability of getting blood clots goes up. So there is a trade-off. All right, that's the allele of the day, celebrating human genetics. I have something more for you soon. Bye.